I'm Mark Miller. I represent Google on the EcmaScript committee, and I helped to design the latest JavaScript standard, EcmaScript 5. One of our goals in designing EcmaScript 5 was to support secure mashups. I'll be explaining what this kind of secure programming is, how to use EcmaScript 5 well to engage in it, and how, because of limitations on what we were able to accomplish in the standards committee, why there is still some remaining hazards which are tricky, which can render your code insecure if you don't know about them, and some patterns to engage in to help you avoid running into those hazards. So I'll first be explaining what I mean by the secure mashup problem. We're dividing it up into two subproblems, which I'm calling the offensive code problem and the defensive code problem. And then I'm going to talk about the sequence of versions of JavaScript standards, starting with EcmaScript 3, which has been standard for most of the last 10 years, and EcmaScript 5, which has a strict mode, and then SES, which is secure EcmaScript, how it is built on ES5. Then explain, so SES is basically a library you load on top of a conforming ES5 browser. Then I'll explain how to use SES to do secure programming, go through some remaining hazards. And this part of the talk is interactive. This part of the talk, I'm going to be posing some riddles to the audience. Only the first riddle is really about arcana of JavaScript, requires some prior knowledge of weird edge cases in JavaScript. The other riddles, I'll be everything that you need beyond simple object-oriented programming, even if you're not that familiar with JavaScript, I'll be presenting during the talk. So please help find vulnerabilities in the examples that I'll be showing before I show the vulnerabilities I have in mind. And as we go through these examples, we'll be learning what the hazards are and how best to avoid them. Now, part of the point of this is to learn is that if you want to write properly secure code, properly defensive code that defends against attackers, you also have to learn partially to think like an attacker. So this is a new set of skills that's not very common among just sort of normal object-oriented programming. But these new skills will open up this new world. And I want you to understand the apparently difficult problems you'll be seeing as just a continuation of this history of software engineering, where throughout the history of software engineering, we've learned that many things that we thought were initially attractive turned out to just be tar pits of complexity and problems and sources of bugs. We used to think that it was good to use gotos. We used to think that it was good to use pointer arithmetic, that threads and locks were an easy way to turn a sequential program concurrent. We've also learned techniques and patterns, like if you're in a language in which arrays are indexed with zero index origin, it's good to use closed open intervals because these things tend to go well together. That by using those techniques together, you tend to avoid off by one problems. And all of these things, when we were starting out programming, it took a while to learn. It took a while for the field as a whole to learn these lessons. We've learned in web programming that rather than form HTML by using string append to append little tags together with data, if you use string append, you were going to have cross-site scripting vulnerabilities everywhere. So instead, use manual encoding. Always encode your data before placing it into the string. But then we found that manual encoding was too hard. It was too hard to really remember, because these languages nest within each other, what the right encoding was. We learned further techniques of how to, and tools, building auto-escaping mechanisms into our templates and to our quasi-literals. So this coevolution of the skills that we need to practice some field of engineering in a safer manner, in a way that's less hazardous, co-evolves with our tools. And this is not unique to software engineering. If you remember when you were first learning how to drive, as a student driver, you had to think really hard when you were first learning how to drive. not to run over that curve, not to hit that tree. But as we gain experience learning how to drive, as we learn these things become second nature. Without any longer needing to think about the hazards, we're now have learned over time to drive safely, not by ignoring those lessons, but simply by having the lessons become second nature. So now we can be thinking about our destination rather than always be thinking about how to drive safely. And our cars, our tools, have co-evolved with our experience about what skills we need to learn. So, for example, anti-lock brakes have made it easier to learn the skills that you need to drive safely. Our cars are basically our IDEs for driving. Okay, so the mashup problem sounds like some specialized problem. I mean, which of us have ever tried to do mashups or secure mashups? What I mean by mashup in this talk is actually much more pervasive than it seems. Mashups are everywhere. Every time you include a script on your page that's written by someone that you don't have good reason to trust, that you don't have complete knowledge of what the script does, you haven't audited the script yourself, every time you do this, you're mixing together code onto your page from multiple other sources, and these scripts might be malicious, but more interestingly, they might simply be vulnerable in such a way as to present new opportunities for an attacker. So, for example, you might just be bringing in some little math library in order to do matrix multiplication. If you just do it today by saying script source equals this matrix math library, and then you call matrix multiply with your two matrices, if the script misbehaves, well, obviously it can simply multiply the matrices badly or throw an exception or return to you something other than the product matrix. But why is it that this matrix multiplier, all I wanted to do is have it multiply two matrices? Why can it now hijack the accounts of my users? Why can this matrix multiplier now abuse my users' cookies and send information out over the internet, engage in phishing, etc.? So that's the problem we want to solve. We want to be able to bring scripts onto our page for all sorts of reasons, and to be able to have the script be given the abilities to do what it needs to do to serve our purposes, but limit the amount of extra authority beyond that it's given that's an opportunity for abuse. So I'm going to present this idealized trivial mashup scenario that's really the scenario we're going to repeatedly revisit to make these issues clear. In this scenario, Alice is the set of objects in control of the page. That's the thing that got loaded first. And Alice is going to load the source code from Bob, which is the string source code for a JavaScript expression from some site B that she doesn't trust. She's going to load the source code for Carol for some site C that she doesn't trust. She's going to do this, and then she's going to take this in both cases and evaluate them. Now, this is very much like saying script source equals to a URL on site B and a URL on site C, but Alice is going to do it this way so that Alice is in a position to exercise more control over what these scripts do. But at the moment, we're not exercising more control yet. We're just doing things the old-fashioned way, and the dangers here are equivalent to the dangers of loading it with the script tag. So, in order to continue with our scenario, let's move Alice out of the way. And now let's say that Alice creates a counter object, and the counter object is simply an object with an incr method that increments the internal count variable and returns the result. A decr method that decrements the internal count variable returns the result. And the incr and decr method are both manipulating this count variable. And what Alice then does is gives Bob access to the counter as a whole, and gives Carol access just to the decrement method of the counter. So That's our scenario. And what the intention that Alice's code has expressed in this scenario is she has enabled Bob, the set of objects that came from evaluating the Bob code, she's enabled Bob to count up and see the result, and to count down and see the result, and she's enabled Carol only to count down and see the result. The goal here is to go from this scenario where Bob and Carol can do these things but can do many other things, to go from there to a scenario where Alice can ensure that Bob can only count up and down and see the result, and that Carol can only count down and see the result. It's the addition of the only that's the critical thing we're trying to achieve with these techniques. So if we don't do anything special, if we just do this with JavaScript and the web as it exists today without taking any special precautions, one way in which Alice fails to achieve the goal is that Bob, being given access to the counter, can simply replace the decrement field of the counter object with its own evil function. And then when Carol or Alice try to invoke the decr method of the counter object, they're invoking Bob's evil method instead. So we call this, so the issues raised by this attack are the issues that we call the defensive code problem. How can the counter defend itself from this kind of attack? But today, the bigger form of attack, the bigger danger, is that Bob can, without interacting with the counter at all, simply by the fact that he's been evaluated and is present on the page, can do all sorts of other damage. He has complete access to the window, to the document cookie, to the XML HTTP request. He can abuse your cookies. He can hijack your account. He can do all sorts of crazy things. So, as Doug Crockford says, a mashup is a self-inflicted cross-site script. In order to do secure mashups, we have to be able to engage in self-inflicted cross-site scripts safely. We have to see this as an opportunity rather than only an attack to be vulnerable to. The offensive code problem is one where secure EcmaScript, for reasons I'll be explaining, can actually solve the problem. That's a problem that can just be solved for you by the platform you're running on. Things aren't so happy for the defensive code problem. The defensive code problem, the most that the platform can do is to support you in writing code that defends itself. But in order for abstractions to be properly defensive, successfully defensive, requires understanding of the semantics that you're trying to achieve with the abstraction. So SES makes it possible to solve the defensive code problem. It does some things to support you, but there are hazards that remain. You can mitigate those hazards with patterns that I'll be showing, but this is still a new skill. So I don't, in listening to this talk, I don't want you to just learn the specific patterns. I want you to start to get a sense of the skill that was behind the effort to come up with these attacks and come up with these patterns as ways to avoid these attacks. Because there will be many other attacks and need for mitigating patterns beyond the ones I'm presenting today. Okay. So the offensive code problem is basically the abuse of globally available authority. It's by using document and window and XML HTTP request, there's just lots of authority lying around, lots of effects that you can cause by simply accessing this globally available state. And what we want to do is deny by default any ability to cause those effects. There's also, in a JavaScript world, there's a set of primordial objects, by which we mean the built-in objects that already exist prior to any JavaScript code running on that page. So like object.prototype, array.prototype, math, JSON, all of these things start off completely mutable, and therefore code in the page can poison these prototypes, can replace object.prototype2string with their own evil function. And since everything uses object.prototype2string, it can cause all sorts of other non-local havoc elsewhere on the page by virtue of this implicit sharing of these prototypes. And also, the global scope itself, even when you remove the dangerous things like window and document, just the things you're supposed to use, if you overwrite those global variables, for example, if Bob replaces the JSON object with one that has an evil parse method, then once again he can disrupt the activity of other innocent code sharing the same page. So given an EcmaScript 5 environment, and I'll be explaining what the issues are in EcmaScript 5 and what are the crucial differences in EcmaScript 5 versus previous versions of JavaScript, but that's coming later, so bear with me. Given an EcmaScript 5 conforming platform, this init SES script turns it into a secure EcmaScript platform. You just do the script source equals to include this script at the beginning of your page before any other JavaScript on that page runs. And what that script does is it takes these 7 steps. I'm not going to go through all 7, but let's start at the end and work backward a little bit. So EcmaScript 5 has a new primitive called object.freeze. And object.freeze locks down the properties of the object you apply to. It makes those properties not writable, and it prevents new properties from being added to that object. So the last thing that init SES does is it goes through all of the primordial state that's defined by the JavaScript standard, basically everything other than the browser-specific environment. It goes through all those objects, and it freezes everything it encounters. It traverses and freezes everything in that primordial environment, so it's all locked down. So there's no longer any mutable state left among the state that's among the objects that are implicitly shared by all the code on the page. Before it does that, it replaces the global eval function and the global function constructor with safe alternatives. I'll talk here only about the eval. The replacement eval, which wraps the original, imposes only 2 restrictions. It enforces that all code that it evaluates is evaluated as EcmaScript 5 strict code. That's a mode of EcmaScript 5 to be explained shortly. And it enforces that the script being evaluated can only name the global variables on our whitelist. The global variables on our whitelist include all the globals in the JavaScript standard, array, object, JSON, math, etc., but doesn't include any of the browser-provided globals that enable a script to cause external effects: window, document, XML, HTTP request. Also, when you evaluate a script, the script being evaluated expects the top-level binding of this to be the global object. That's one of the rules of JavaScript. Normally, the global object is the window itself. The safe eval that we're creating, where we want to always deny access to the real window. So instead, we make a virtual global object that just contains the global variables on our whitelist. And all those global variables are frozen so that they're no longer assignable. Okay. The net effect of that set of rules taken together is that having done init SES first before doing this, when Alice evaluates Bob using the safe evaluator, Bob can't name window, he can't name document. All the objects it has implicit access to are all completely locked down. All the state is frozen. So at this point, Bob cannot cause any effects to the world outside of himself. The result of evaluating Bob is that you have some subgraph of objects which effectively have no pointers out. It's completely isolated. And likewise for Carol. So we show that by showing the thicker boundary. Alice, of course, by evaluating Bob, obtains a reference to whatever value that expression evaluates to, which we'll just think of it as the root of the Bob subgraph, and likewise for Carol. So what can Alice, so let's go through the same scenario. So Alice makes the counter and provides Bob with the counter object as a whole, Carol with the decrement method of the counter. And what we've done so far is we haven't changed the counter itself. We've just changed what eval does. So the second set of attacks, which are the really dangerous ones, we've already succeeded at preventing those. Those are the offensive code. That's what the offensive code problem, which corresponds to what's traditionally called sandboxing. But the confinement is much stronger than traditional sandboxing. What we haven't prevented is the corruption of non-defensive code. If Alice has just made a counter in some normal way without doing anything to make the counter defensive, Bob can still corrupt the counter, with the result that Alice and Carol, when they interact through the counter, are now doing something other than what they intended to do. So the defensive code problem has there's several fronts to fight on. One is that the attackers will try to violate the encapsulation, might try to reach through the inker and decker methods in order to get at the private count variable, the private count instance variable of the counter. The attacker might try to tamper with the API surface. That's the attack we just saw, where Bob replaces the inker method with his own, decker method with his own evil method. There's a more general form of attack, and this one's the one that makes it clear why a platform can't solve the problem for you, which is every time somebody writes a program, there's a certain set of assumptions they're making about what the runtime situation is within which their program will be executing. If those assumptions can be wrong, if the attacker can make those assumptions wrong in ways that the programmer did not anticipate, the program can go awry. It can be proceeding in a corrupt manner. And the nature of that corruption might be further exploitable by the attacker, and in particular might be further exploitable in order to violate some further assumptions upstream, causing yet more corruption, causing this contagion of corruption. Okay. So how should we write the counter? Well, how do JavaScript programmers write counters today? Right? In general, how do JavaScript programmers write objects today? Well, the most common pattern is something called the classic JavaScript prototype inheritance pattern, where you make a constructor function that acts like the class, capital counter here. It initializes the state of the instance. You make a prototype object that has the methods, and every time you call the constructor function, it creates a new counter instance, which is each of the layers here. So the multiplicity of layers represents the multiplicity of instances every time you call counter. The assignment over here is initializing a new count property on each counter with the value 0. Each counter inherits from the counter prototype that has these inker and decker methods. Now, for purposes of this talk, all the rest of the complexity on that slide, we can just get rid of it. For the rest of the talk, we don't care about it. We do need to understand how JavaScript inheritance works in order to understand the attack possibilities and the defense possibilities. So when somebody goes to increment the counter by calling the counter's increment method, by saying c.incr, what actually happens? Well, this is not, you can think of this as being one expression, but you can think of it as having c.incr by itself as a sub-expression. So this sub-expression, what it's doing is it's starting with the C object and looking up the incr property. Well, C doesn't have an anchor property, so it climbs the prototype chain, and then it sees, does this object have an anchor property? Aha, it does. And the anchor property is the function that this function expression evaluates to. So that's the method, is this function over here. The open paren, close paren call the function, as you would expect. And over here, in this case, the function has no arguments. But if it had arguments, obviously you'd put it between the open paren and closed paren. And the corresponding explicit parameters go between the open paren and closed paren here. In this case, once again, it's empty, but that's where they would go. And all that is completely conventional. No surprises there. The surprise is this function mentions a this. Where does the this come from? Well, in JavaScript, this is really has the semantics of an additional unnamed parameter that all functions have. And when you write out a function call in this manner, JavaScript considers it to be a method call and picks up the value of this part of the subexpression, and besides using this value to look up the value of the anchor property, it additionally passes that value as the implicit this argument, so that when anchor runs over here, this is bound to the instance that you called this on. So this plus plus this dot count increments this count. The reason I say it really has the semantics of an implicit parameter is JavaScript provides you all the flexibility that comes from treating it as a genuine parameter, just that you have to engage in some syntactic workarounds in order to make use of that expressivity. So if you say c.anchor open close, as we saw, that's a method call. In JavaScript, if you index into C with square brackets and you put a expression in here, if that whatever value that expression evaluates to, that's taken to be the property name. And so for example, if that's an expression that evaluates to the string anchor, then that still looks up the same anchor function. And even though you looked up the anchor function with square brackets rather than dot, JavaScript still considers this a method call. So this is still bound to C. Even if you surround the c.anchor or the c open square bracket anchor with parentheses, you still haven't broken it up into a separate lookup and function call expression. It's still jointly together considered a method call. If, on the other hand, you say c.anchor, you just do the property lookup by itself, obtain the value, and then separately call the value as a function, now it's considered a genuine function call. And when the function gets run, this gets bound to undefined. The least verbose way to force JavaScript to consider it to be a function call when a function call is what you meant is to use a comma expression. A comma expression is one that has two sub-expressions. The one to the left of the comma is first evaluated. In this case, it's the useless expression one. It does nothing. And then the expression to the right of the comma is evaluated. It's evaluated to a value, and the value of the right-hand expression is the value of the comma expression as a whole. So now that you're calling the value of the comma expression as a whole as a function, now JavaScript considers it to be a genuine function call, and this once again gets bound to undefined. And then finally, to have the full expressivity, if you obtain that function, you put it as a property in a separate object, and then you call it as a property in a separate object. And this other object is not at all a counter. It might be a completely unrelated object. The anchor method from the counter abstraction still gets called with this completely unrelated object bound to its this. And you can also do that explicitly by using reflection. All functions in JavaScript have an apply method. And we'll be using a convenience here called apply fin, which is like the apply method, but that just takes the function to be applied as the first argument. takes the implicit this parameter, makes it explicit as the second argument, and takes the list of arguments as the third argument. So this is a magic incantation that I won't be explaining for creating your own convenient reflective apply function, and it has the following identity. That any time you would have written object dot some property name and then some list of arguments, that's equivalent to saying apply fin with that function, the object from there as the this binding and this list of arguments. Similarly, a simple function call is equivalent to saying apply fin of this function undefined as the this binding and this list of arguments. Okay. Now that we understand the rules of method calls and this binding in JavaScript, we can go back to the conventional classic JavaScript pattern and see what the hazards are. Well, one hazard is a confusion attack. As we saw, Bob can simply obtain the incr method from the abstraction and apply it to some completely other object that the incr function did not expect to be operating on. And in this case, maybe it doesn't do any significant damage, but there are cases where it can cause damage. And in general, if you can force the code to operate on objects that have very, very different operation than the code was written to expect, you can cause confusion. Also, in order for incr and decr to be able to increment and decrement the count field of the instance has to be writable. Otherwise, incr and decr can't write it. But in JavaScript, if incr and decr can write it, anybody can write it. So Bob could simply store -infinity in there, putting it into a state that the author of the counter did not expect. And now, no matter how many times Alice and Carol increment and decrement it, it stays -infinity, because -infinity plus 1 is still -infinity. So our first lesson is, for writing defensive objects, for solving the defensive code subproblem of the secure mashup problem, the classic JavaScript prototype pattern is a bad way to do objects. And we've also learned that this implicit this parameter is very treacherous. Whenever we see this in a piece of code, we should always think to ourselves, how can this be abused? Okay, so if we're not going to write objects the traditional way, the classic way, what should we do instead? Well, in Doug Crockford's book, JavaScript, The Good Parts, which I highly recommend, he explains what he calls the objects as closure pattern. So over here we have an example of it. It's not yet defensive, but it's defensible. Starting from here, we can take some small incremental steps and succeed at defending this. So over here, JavaScript really has these two basic abstractions, the function and the record. So make counter, we're just defining a function. And every time you call make counter, it creates a new count variable. Now it's just a lexical variable, initializes it to 0. And then creates and returns a record, which is the open paren close paren over here, with two fields, incr and decr. And the incr field is the value that this expression evaluates to. The decr field is this one. Notice there's no this dot count either here or here. Rather, both the incr and decr are just manipulating the count variable that they have in scope. So over here, the reason why this pattern gives us back the power of object-oriented programming is we've got a record of closures. Closure is just a fancy name for the functions that these function expressions evaluate to. A record of closures hiding state. The state is this assignable count variable. That corresponds to an object of methods. So the object is the record. The methods are the incr and decr functions hiding instance variables. The instance variables of this object are simply the count variable that both of these functions capture. And we show this over here in our notation. Lexical nesting is shown as spatial containment. Multiple instantiation, again, is shown as multiplicity of layers. Every time make counter is called, it creates a new triple of an incr method, a decr method, and a count variable that they share. And incr and decr are shown touching the edge of the layer because they're accessible outside the layer, count is now shown internal to the layer because no one can get at it other than the Inker and Decker method of this counter. Okay. Notice that we relied on lexical scoping, and so far, because records in regular JavaScript, in old JavaScript, are mandatorily mutable, meaning that there's nothing you can do to prevent assignment to field of records, it was impossible in EcmaScript 3 to write a defensive abstraction. It was literally impossible. EcmaScript 5, by bringing in object.freeze, fixes the mandatory mutability. It also fixes all of the scoping confusions. It fixes them in 2 steps. There were 6 ways in which EcmaScript 3 violated normal static scoping, the static scoping that you expect of any sane language. The first 3 of the scoping confusions are just fixed going from EcmaScript 3 to EcmaScript 5, end of story. And then the next 3 scoping confusions are additionally fixed by opting into strict mode. You opt into strict mode by putting the string use strict at the top of your program. And that makes that program interpreted as a strict mode program. All the functions it defines are considered to be strict functions. So I won't explain what these scoping confusions are, because from here on in the rest of the talk, since you can easily repair these and give yourself sane scoping rules, for the rest of the talk I'll be assuming that you have done so. So going to EcmaScript 5, object.freeze addresses the mutability issue, addresses the scoping confusions. There's also additional encapsulation leaks that EcmaScript 3 and EcmaScript 5 non-strict have that still make it impossible to defend this counter. So as I said, object.freeze will take care of the mutability of this top-level record. It still leaves these 2 functions as being objects in JavaScript that Bob could add new fields to, add new properties to, that Carol could then read, or vice versa. So it still opens up communications channels between Bob and Carol. That's the unexpressed mutability. So Bob and Carol, by sharing the object, can add new properties and engage in communication that is not within the behavior that Alice was trying to enable. We're violating the constraint that Bob and Carol can only communicate through the counter abstraction. There's a scoping confusions which we fixed with EcmaScript 5 strict, and there's further encapsulation leaks. So let's see, how am I doing on time? I'm going to skip these encapsulation leaks, just making the point that by putting use strict at the top of the program, it also fixes the encapsulation leaks. Once your code is in EcmaScript 5 strict mode, you've got real lexical scoping, and your functions are really encapsulated, so no one can reach through Inker and Decker in order to get direct access to the count variable. So now, to solve this mutability of the functions themselves that Bob and Carol could add new properties to, the SES, init SES gives you a library of new abstractions. One of them is this def abstraction, which is an abstraction for a pattern using object.freeze to basically transitively freeze everything reachable, starting from the record that's being frozen. So object.freeze itself just does a shallow freeze. It freezes the record itself. Def will additionally freeze these functions and freeze the properties hung off of these functions, in particular those functions .prototype, if you know what that is. If you don't know what that is, don't worry about it. So the net effect of putting useStrict up here, of being in SES and using def over here, is that we now have a tamper-proof object. The object's behavior is only the behavior expressed by its code, of lexical closures, of these function objects having real, obeying sane scoping rules, encapsulating states, successfully preventing any other access to the count variable. That gives us a defensive object. And now we go back to the goal we set out to do, and for this simple abstraction, Alice has achieved her goal. We have succeeded at getting at imposing the restriction that Bob's only interaction possible with the world outside of himself, once Alice has set up this situation, is the ones that were expressed by the code that Alice wrote. She successfully prevented any further behavior beyond the behavior whose intention was explicitly expressed by her code. And the lessons we've learned is, again, Alice succeeded at this by having the abstractions that needed to be defensive, the ones that were exposed to potential attackers, avoid using this, avoid using prototypes, using the object disclosure pattern, or Tom Van Cutsem and myself have created a library called traits.js that's available at traitsjs.org. That's a whole nother talk. But the problem with the object disclosure pattern by itself is it doesn't give us the flexibility of subclassing that we're used to, that the prototype inheritance does give us. Traits.js gives us back the flexibility of subclassing and more, but it does it without introducing the dangers that we get by using the classic prototype pattern. The problem with both object disclosures and traits.js is it's somewhat more expensive. It causes extra allocations compared to the classic pattern. So it's up to you to decide when your security needs are sufficiently important that they're worth the extra allocations. And also, not only do these things address the this rebinding dangers, they also address the mutability leakage. They lock things down, so the only things that are mutable are things like the internal count variable that were intended by the abstraction that you wrote to be mutable. Okay. So, I believe I've given you, given that you know basic object-oriented programming, have just sort of very basic knowledge of just sort of the basics of JavaScript syntax, but don't know any JavaScript beyond what I've explained in the talk, can you spot the attack here? Well, before I tell you the attack, let me tell you my interpretation of what this code does and what it is that Alice intended this code to mean. And let me give you all a moment to read it so that when I tell you what I think the code is intended to mean, you can check it against your own reading of the code. Oh, and if anybody who has not yet seen this in prior papers or whatever, if anybody who doesn't already know this example, if you can spot the attack, please raise your hand. Okay? No. Good guess. I like the idea. If you call get with no arguments, then a parameter that's bound to an absent argument gets implicitly bound to undefined. So this return array sub I, the I here will be the value undefined. The square brackets will coerce it to a string, so it literally coerces to the string undefined. And then you'll be looking up in the array the value of the property named undefined. The array in this case will not have a property named undefined. So when you look up an absent property, you actually get the undefined value back, not the string undefined. So in this case, get with no arguments will return back the undefined value. Okay. Now let me tell you what I think Alice meant when she wrote this code. Oh, sorry. Go ahead.
Well, I was just going to guess you have not locked down the table itself. Maybe not add a property or something to the table.
So I have locked down the table. That's the def abstraction. The def is the thing from the SES library that does the recursive object.freeze with everything reachable starting from that record. Yes?
Can you return some sort of function closure as I? Oh, it's B and then. Oh, yes. So I is equal to push. B is equal to function this, or this dot, whatever.
Congratulations, you win. Now let me, yes. I'm very impressed. I've had people that know JavaScript really intimately and have thought about security for a long time look at this example and not see that. Okay, so now let me tell you what I think the code is intended to do. It's a table abstraction built on top of an array that Alice intended to encapsulate. So by giving Bob access to the table abstraction, she wanted Bob to be able to call add, store, and get, but wanted to deny Bob direct access to the array. How can Bob instead steal the array from the table, violate the encapsulation that Alice intended, even though all of this is in SES, and Alice already followed our first recommendation, which is to use def? Well, here's what Bob's code does. Creates his own local stash variable, calls table.store with the first argument here being the string push. The second argument being this function. We'll come back to what the function does here, but let's just first of all concentrate on what store does. So over here's the store function. It says array, open square bracket, the string store, close square bracket, gets v. So that stores the v value, the function that we're being passed as the second argument. It stores that as the value of the push property on the array instance. So far, no damage has been done, but the array instance has now a new push property. When Bob then calls table.add, what does add do? Well, it calls array.push. The author of this program wrote the program expecting array.push to be the genuine push method inherited from array.prototype. The author of this program, knowing they were in SES, thought that assumption was safe for the following two reasons. Array.prototype itself has already been frozen by the SES initialization, so nobody can replace array.prototype.push. In addition, the array is fresh. The array is newly created here. It wasn't something that was accepted in from the outside. So it really seems like here's an array that table newly made. It never gave it out. So when I invoke the push on it, it must be the genuine push that inherited from array.prototype. Bob, by calling store with the push string, has violated that assumption, has confused the code, has caused the logic of the code to do exactly what it says, but not what its programmer meant. The programmer made an assumption that was not justified, and the execution now proceeds in a corrupt manner. And the particular corruption is that the function that Bob stored here, this function over here, gets invoked as the push method on the array. This is considered a method call. Since it's a method call, the array, the method is called with the array being provided as the implicit this argument to be bound to the implicit this parameter of the function. So that's the this here, which Bob simply stores into his stash, and now Bob has obtained direct access to the array. So there's two, yes?
I'm sorry, I might be missing something, but so why is it that they were successful in overriding the push even though it locked down?
Okay. The reason is that what's locked down is array.prototype.push. So let's go back to our picture of JavaScript inheritance. Yeah. So over here we have a counter that inherits from a counter prototype. The methods are on the prototype. In like manner, what's going on in this example is we have an array instance, and it inherits from an array prototype. The array prototype has a push method. This thing over here is completely locked down. Nobody can modify it. This array must not be locked down, must be mutable, because add and store must mutate it. So the table code on purpose does not freeze the array instance. Does not freeze the array instance. because both of these things must mutate it. But the programmer assumed that it was still safe to call the push method on the array, because if nobody has access to the array, then the push method that I'm invoking here must be the one that I inherited from object.prototype. That's the assumption that's wrong, is the array instance now has its own property named push, whose value is this function. So the method is looked up on the instance, not from the prototype, but it's still invoked as a method, providing the array itself as the this binding. And obviously, what Bob passes as the argument to add at this point does not matter at all. Okay, so it turns out that I thought this was an attack until I posted this puzzle on the ES discuss list, the EcmaScript discuss list. Everybody that I showed it to, for which I explained this attack, also thought it was an attack. Once I posted it to the EcmaScript discuss list, Dave Herman realized that this attack itself happens not to work because, on a conforming browser, although it happens to work on many existing EcmaScript 5 browsers, because of an obscure legacy issue in the EcmaScript 5 semantics that I'm not going to explain in this talk, but it's the kind of detail that since in this case it prevented an attack rather than enabled an attack, it's not one that I feel compelled to explain. But the interesting thing is here that the pattern that I learned from thinking about this attack succeeded at defending against the attack that neither I nor anybody that I had talked to prior to my posting this riddle on the EcmaScript discuss list had ever anticipated. Jorge Chamorro, and excuse me if I mispronounced that, I've only seen the name in email, on the EcmaScript discuss list, posted this alternative attack. This one works even on a conforming browser. This one relies on this other peculiarity of JavaScript, which I will explain because it surprisingly enables attacks rather than surprisingly preventing attacks, which is that on some browsers, the non-standard property name _proto is another name for the pointer inside each object that points to the object that object inherits from. That upward pointer that I was showing on the diagram is also non-standardly on some browsers known as prototype. And on those browsers, you can also change what object a given object inherits from by assigning to prototype. So in Jorge's attack, by storing into _proto a new record which has a property named push that has the same attack code in it, now the array instance no longer has its own property named push. It now goes back to the situation of, is this push an inherited push? In this case, it is an inherited push, but it's not inheriting from array.prototype. It's inheriting from the new parent of this array instance, which was reparented by the store over here with the I being bound to _proto_. So, if you have to think through, this is the point of patterns. You have to think through this level of attack every time, which experts could look at and puzzle about and not spot, then you'll never write secure code if you have to think about it each time. The point of this talk is the first time we encounter things like this, we think, okay, what can we do that avoids this category of problem in general? Just like, we went through lots of pain with gotos leading to spaghetti code, and finally we learned a set of structured control flow patterns that once we learn them and start practicing them, we no longer have to think about all the dangers specific to this kind of spaghetti and that kind of spaghetti. So, in this case, the other danger here, the reason for the danger, the reason why this attack works, and this is the hint that leads us to the pattern, is this confusion that's everywhere in JavaScript between objects as mutable records, as mutable string-to-value mappings, versus the objects as API surfaces, where the properties are the API of the object. When we say array.push here, we're intending to invoke the array's API. When we say array square bracket I, we're intending to use the array as a container, as a mutable container of values. So the first pattern is that if the kind of container you're using an object as is an array where you're indexing into it numerically, never say bare open square bracket for doing the indexing. Always say square bracket plus. Plus in JavaScript is a unary prefix operator that coerces the argument to a number. And this will prevent whatever I is here, it'll prevent it from colliding with the expected API surface. So in this case, I will be the string underbar, underbar, proto, underbar, underbar. The plus I will coerce it to the number nan. The square brackets will coerce that back to the string nan. So you're still going to get something that's a little surprising, which is now the value of the array's nan property is the function. But objects don't generally have part of their API be named nan, so this has successfully separated the two namespaces. Okay. Second puzzle. This is actually the last puzzle. In this case, Alice wants to create a publish-subscribe abstraction, basically a topic that you can publish to or subscribe to that exposes a publish method and a subscribe method. They both share a subscribers list. And what Alice wishes to express, the policy that she's trying to express in her code, is that Bob can publish or subscribe, Carol can only subscribe, and that whatever is published by invoking the publish method, whether by Bob or by Alice, that all subscribers see those publications in the same order. That if A was published first and then B was published, everyone who subscribes first sees A and then sees B. So here's a simple abstraction that seems to do the job. It doesn't itself use this anywhere. It's not using prototype inheritance. So we've learned our lessons. We're using object closures. We're keeping our state in a lexical variable that we're not exposing. We're using def to do the transitive freezing. We are doing subscribers.push over here, but anytime we index into subscribers, we're doing it with open square bracket plus. So we've learned the lesson from the previous attack. So let's walk through what this code does. Every time anybody subscribes, the subscriber is also, this is another way to think of this, is like the listener pattern or the observer pattern. So the subscriber is like a listener or an observer. We're just adding it to our list of subscribers. And anytime anybody publishes, we go through all the subscribers in our list, we look up each subscriber, and we call it giving it the publication. Okay. This code is vulnerable to 3 attacks. There are 3 ways in which Bob can subvert Alice's intention here. Can anybody spot any of the attacks? Yes, there is. Very good. That is the first attack. So Bob can subscribe an evil subscriber. As we saw, even when you look up a property with square brackets, if you look it up and call it, right there is one intact expression. JavaScript considers that to be a method call rather than a function call. So when Bob's evil subscriber gets called, the subscribers list itself is passed as the this binding. You're looking up that subscriber as if it's a method on the subscribers list, and you're calling it as a method. It's this gets bound to the subscribers list. So what Bob does is he always takes, Bob's evil subscriber always puts itself at the beginning of the list. So if somebody else had subscribed prior to Bob, Bob's going to wipe him out, just go back to the beginning of the list, and then an array, if you set the array length to 1 in JavaScript, that truncates the rest of the array, so you can get rid of all the other subscribers. In this case, Bob could actually do more damage than I'm showing here because he could actually pick up the other subscribers, for example, the Carol subscriber, and call the Carol subscriber with bad data, with things that were never published. But let's just focus on this danger. So the lesson from here is always be careful not to confuse calling a callback function with invoking a method. You want to keep those two things straight. Just like plus separates API lookup from numeric index lookup, we also want to separate, be clear that function invocation, method invocation are again not confused. So since we wanted to call the subscribers as functions, the most compact way again is to use our comma expression, and that successfully thwarts the first attack. So, our first attack is now prevented. What are the remaining attacks? What are the remaining ways in which Bob can still violate Alice's intention here?
Modifying array prototype push?
No, array prototype push, since we're in SES, that's already locked down. It's already made completely immutable.
Well, if he passes in a subscriber with this, won't he get an undefined?
Yes, he will. The reason this attack fails is that this here gets bound to undefined. Undefined doesn't give Bob any inappropriate access.